Right, so this first question is about magnetism, and it says which two materials are magnetic? Well, carbon isn't magnetic, cobalt is magnetic, copper isn't magnetic, nickel is magnetic, and sodium isn't magnetic. The only other element that is magnetic is iron. And remember that steel would also be magnetic because it is made of iron. So just remember that the magnetic materials are iron, nickel, and cobalt. They are the only three elements that are magnetic. Right, describe how you would find the magnetic pattern of a permanent bar magnet. Well, what we would do is we would get a magnet with a north and a south pole, and over the top of that we would put a piece of paper and we would scatter on some iron filings, and the iron filings would line up stronger at the poles, and then you would see some kind of pattern around where the field lines are, something like that. And what would this show? Well, the first thing, so let's talk about how you do that. So you'd position the magnet under the paper, sprinkle filings on top, and then the filings would align on the paper in the position of the field. An alternative to this would be that you get your magnet on another piece of paper and you use some plotting compasses and you position them going around the magnet, and these would point towards the magnetic field. So if we had a south pole here, you would get a compass needle pointing something like this, and it would point away where you have the north pole. So the compass needles would point towards the south pole and they would point away from the north pole, and they would align themselves again in the direction of the magnetic field. And remember, the magnetic field looks something like this. And it always goes to the south and away from the north. So an arrow here would go to the south and to the south pole. Right, so this is about the investigation, and it says a student investigates how the number of turns of a wire on a solenoid affects the strength of the solenoid. To test the strength of the solenoid, she looks at how many paper clips it could lift. So the paper clips are going to be made of something like iron, and because this is a magnetic material, when you turn the electromagnet on, it will attract to the paper clips. Now remember, this is a pole, so this might be a north pole and this might be the south pole. So this is the poles of an electromagnet. And when you have a coil like this, you get a magnetic field just like a bar magnet coming straight through, and it would go around the bar magnet, something like that. So if we had a north pole, it would be moving away from the north pole and towards the south pole, something like this. So I'll just remove that ink. Right, so we've got this data here and it asks us to plot the data onto the graph. Now remember, when plotting data we always plot the mean, and the mean is shown here. So at 30 you can see it is 12, so we go up 2 squares to there, and at 40 it is 15, so we go up to 15. At 50 we've got 21, so we go up to 21, and so on, and 60 is 25, which is there. And this should give you a directly proportional relationship. Remember, directly proportional means it goes through the origin at 0, 0. So describe the pattern in the graph. Remember, when we're describing pattern, we always talk about this variable and how it affects this variable, because this is the independent variable and it's how it affects the dependent variable. So increasing the number of turns increases the mean number of paper clips picked up. The second mark is going to be for the fact that it is directly proportional. So this relationship is directly proportional. Why is that? Because we've got a straight line that goes through the origin. The number of paper clips that are picked up, well, to work this out at 80, we would have to continue this graph on. Now remember, if you've done this with a pencil and a ruler, you'll get an accurate plot, but if I try and carry that on to somewhere like that, we're going to get roughly about 32 paper clips. Right. The next question is about a motor. So we've clearly got a supply here. So this is our 1.5 volt cell, and this is going to then create a motor effect here. So once the coil is spinning, one side of the coil is pushed by a force, and the other side is pulled, so the coil continues to spin. So you have two changes to make it spin faster. Well, we could increase the voltage. Instead of being 1.5 volts, we could make that greater, or increase the current. So to do that, we would have to increase the voltage. We could have more turns. If there was more turns in this coil, that would increase the strength. Another thing we could do is that we could increase the strength of the magnet that is here. So increase strength of magnetic field. We could also make the area that is inside the field greater. So if you have a coil like this inside a magnetic field, if you had a greater area such as this inside the field, then you would have more wire cutting the field lines. So the area that's actually cutting the magnetic field will affect the strength of the electromagnet. So suggest two changes to the electric motor, each one which would make the coil spin in the opposite direction. Well, if this was positive and this side was negative, then we could flip this around. So if we swap the terminals of battery, okay, this is often called a polarity. So that's whether it's positive or negative on each side. And the other thing we could do is swap the magnetic poles. So if this was a north and this side is a south, we could make this side a south and this side a north. If we swap the magnet around or we swap the battery around, it's going to spin in the opposite direction. Right. The next question says, diagram 1 shows a magnetic closure box. When open and shut, it is a box that stays shut when it is closed due to the force of two small magnets. Diagram 2 shows the two magnets. The poles of the magnets are on the longer faces. So we know this is a north pole and this is a south pole. So we're going to have field lines going from one to the other like this. Okay, and they are horizontal. You can see there's no curvature because we've got a north and a south pole, and we're going to draw an arrow because the direction of the magnetic field always goes from north to south. So it says draw on the diagram the field pattern with the two facing poles. So we've done that, and that will get us 2 marks. The magnets in the magnetic closure box must not have two north poles facing each other. That's because two north poles would repel. Remember the key words. This is attraction, so they would attract, but if they were the same poles, if it was a north and a north, they would repel, and the box would not close. Right, in this next investigation, it says a student is investigating how the force of attraction between two bar magnets depends on their separation. She uses the apparatus shown in diagram 3. So we've got a Newton meter, a magnet, and we're trying to see the force that this magnet is having on the other magnet by pulling it down. So by putting this magnet here, we say got a north pole there, and that is attracting the other one, which is connected to a Newton meter, and that attraction is pulling on the Newton meter and measuring the size of the force. So the pattern is showing that the number of sheets of paper between the magnet, so we've gone from 10 to 20 to 30, so we're increasing the distance of the magnet basically, and it's obviously affecting the reading on the Newton meter, as you'd expect when the two magnets are closest with the least sheets. So we've got only a few sheets and that magnet is quite close to that magnet. As we add more sheets, the magnets are getting further away and therefore the reading on the Newton meter is going to go down. So we're going to describe the pattern and the results. So when we're doing this, if there's 2 marks, you must be very specific. The first one is from 10 to 50 sheets. So basically, an increase in sheets. There is a decrease in force on the Newton meter. So that's going to get you 1 mark. That's 1 point. We're talking about from here through to there. By increasing the number of sheets, we have decreased the force. The next one is from 60 to 120. You can see these numbers are all the same. So from 60 to 120 sheets, there is no change in force. Now it's said describe. I have not explained anything. I've not talked about magnetic strength. All I've done is describe the pattern shown by the table. So when you're asked to describe the pattern, just say what you see in the table. Don't try and explain why that happens. Right, the next question says, no matter how many sheets of paper the student puts between the magnets, the force shown on the Newton meter never reaches 0. Why is this? Well, that's because if this is our Newton meter, and it's connected to our magnet is going to pull on the Newton meter. It's going to pull down because the magnet has got a weight. So any weight is going to pull this down a little bit. So magnet has weight, and the weight is due to gravity. Right, the student is unable to experiment with fewer than 10 sheets of paper without gluing the magnet to the Newton meter. Suggest a reason why. Right, well, if you think about it, the attraction, say we just have one piece of paper here, the attraction between the North and the South Pole is going to be much greater. So at very few sheets, you've got a really strong attraction. And because of this, it's going to be so strong that it's actually going to have a bigger force than the top magnet, if I just finish this off, and the hook, which supports it to the Newton meter. So if this force here is greater than the force actually holding it on the Newton meter, it's going to pull it off the Newton meter and it won't work. So that's the reason. So the attraction between the magnet between the magnets is greater than the attraction between the hook, between the hook and magnet. So that's going to get you 1 mark. So this point here, so what we're saying is this attraction between the two magnets, between the paper, is greater, that bit is greater, that attraction, than between the hook and the magnet, so that's less. So because the attraction between the magnets is greater than the attraction between the hook and the magnet, the hook and magnet would separate before trying to write down here, it's not going to let me, before the magnets split. Okay, right, suggest 3 improvements to produce to the procedure that would allow the student to gain more accurate results. Now on the mark scheme there's lots of ideas, but I'd really like you to stick to the ones that I think are the best answers, because some of them talk about reliability, doing it more than once, and by carrying out things more than once you will get a more accurate result. However, you should really be using the term reliable. So I think the best answers on the mark scheme for this are: to get a more accurate result you should use a mechanical device, to apply the force. So by having a mechanical device, you're obviously going to have a force that is consistent and it is easier to measure. Also, if you have fewer sheets between readings, so we've gone from 10 to 20 to 30 to 40. So if instead of that we went 10, 12, 14, so fewer sheets between readings. Now the number between these is called the interval. So this interval is 2. This interval is 2. The interval here is going up in tens, and here it's gone up in 40s. So if the interval is smaller, you're going to get a more accurate answer because you're doing more testing. So reduce the intervals. Well, I've said fewer sheets between readings to try and make that easier to understand. And the last thing is the same thickness of paper. So obviously you need to make sure the same thickness. If one's like this and then another one is that thick, then it's obviously going to affect the experiment. So it's really important that the thickness is the same for all of the sheets. So what you could do is take one piece of paper and maybe cut it up so you know it's the same thickness. Right, the thickness of one sheet of paper is 0.1 millimeters. What is the separation of the magnets when the force required to separate them is 2.1 newtons? Right, so we know that 2.1 newtons, according to our table, is this part here. So 30. So 2.1 newtons is equal to 30 sheets. So again, I'll look up here. 2.1 newtons gives us 30 sheets. One sheet is 0.1 millimeters. If we've got 30 sheets, then 30 times by 0.1 will give us 3 millimeters, and the answer is 3 millimeters. Right, a student is investigating the strength of an electromagnet, and figure 3 shows 3 different electromagnets. Right, it says, so we've got A, B and C, and clearly with A you've got 20 turns, 30 turns and 30 turns. Right, no more paper clips can be hung from the bottom of each line of the paper clips. Complete the conclusion that the student should make from this investigation. So increasing the number of turns of wire wrapped around the nail will increase. You can see going from 20 to 30 has increased the number of paper clips. We've gone from 4 here, we've got 1, 2, 3, 4, 5, 6 paper clips there. Right, which two pairs of electromagnets should be compared to make this conclusion? Well, we should be using these two because we're comparing A to B because there is a different number of turns. So A and B. And we should also be comparing B and C because they have the same number of turns, therefore they should have the same number of paper clips, which they do. They're both 6. So if we get the same when the turns is the same and different when the turns is different, we know it's the turns that's having the effect. So by changing the independent variable, we've measured the dependent variable, which is the number of paper clips that is picked up. Suggest 2 variables that the student should control in this investigation. Well, they could control the voltage or current. If you changed either of these things, you're going to have a stronger magnet. And also the size of paperclip. By using paper clips that are bigger or have a greater mass, you're going to pick up less. So it's really important that they have the same mass. Okay, so it says in the next question, the cell in the electromagnet is swapped around to make the current flow in the opposite direction. What is the maximum number of paper clips that can now be hung in a line from this electromagnet? Well, we know that it's got 20 turns, so it should be the same as this. So we're going to say it is 4. And the reason is because the strength of electromagnet is going to be the same as 20 turns with current going in opposite direction. The flow of current makes no difference. It doesn't matter which way around it is. And the reason we know that is because we have some evidence here. This has had no effect. So this way it's going that way, sorry, and this time it's going that way, and they both pick up 6. So to add to this, evidence provided by B and C. Okay, right, suggest the maximum number of paper clips that could be hung in a line from the end of this electromagnet. So maximum number of paper clips. Right, if we have 10 turns, well, if we have 10, 20 and 30, well, when we had 30 we had 6, 20 was 4, so we would expect with that pattern it to be 2. Right, a magnetic toy uses a ring shape. The magnets can move up and down on the rod. We've got a north and south here. If these aren't touching, then we know they must be repelling, so that must have to be a north and that must be a south here. If they were attracting, we would then flip these poles around. So the magnetic poles are labeled on label them on B, so I've done that. What would happen if the ring magnet B was turned upside down? So it would attract. Right, so this is what I described before when we were talking about using some compasses, but clearly you can see in this particular one they are not all aligning themselves with the field around the wire, and that tells you that there cannot be a current around the wire. So when this switch is open, they will all align themselves in the direction of the Earth's magnetic field. So when the switch is open, there is no current. Explain why the needles all point in the same direction. They will align in the direction of the Earth's magnetic field. Okay, so that means they will point north. Now the actual north pole of the Earth is the geographical south, and therefore they will point to the magnetic south. So this is the magnetic south, and therefore compass needles point south. Right, there is now a current in the wire. The compass needles change direction. On the figures you draw arrowheads. Now remember, if we gripped our hand around this wire, our right hand, and put our thumb in the direction of the current, which is up there, then we would have the current going this way, and you can see that our hand wraps around this way, so the field is going to go in this direction. So this is called the right hand thumb rule, and basically the current's going that way, so the field circles around like so, and it goes in this direction. So you can see the compass is pointing in this direction here, so here it must be going that way, and there, and like this, because it is spiraling around in a anti-clockwise direction. Right, what would happen to the direction of the compass needles if it was reversed? So if we reverse the current, then our right hand thumb rule, the right thumb would be pointing down, and it would wrap around this way. So therefore the the field would be in the opposite direction, and therefore the needles would point in the opposite direction. So needles point in the opposite direction. Right, figure 4 shows a coil of wire in a circuit. Draw the magnetic field due to the current in the coil. So I talked about this before. When you see a coil, it's called a solenoid. And a solenoid behaves like a bar magnet. So we just pretend it's a bar magnet and we have the field coming out of a bar magnet like so, and then it curves off like this. And remember, because this is the North Pole, it would go away from the North Pole. So all of these would be moving away from the North Pole, and all of these would be moving towards the South Pole. So we've got the South and the North, so the arrows come towards the South like that. And that would get you 3 marks. So remember, whenever you see a solenoid, you just pretend it's a bar magnet and the field will be exactly the same. It goes from the North Pole to the South Pole. Right, the area around a magnet is called a magnetic field. The Earth has a magnetic field. What causes the Earth's magnetic field? It is the movement of liquid iron in the Earth's outer core. So this spinning of iron generates a magnetic field. Right, what will happen in each case when the poles of two magnets are brought together? So if they are opposite, they will attract. And if they are the same, they will repel. You must use those terms. Right, the next question is about a crane, which is an electromagnet. So it shows an electromagnet being used to lift a car in a scrapyard. An electromagnet is basically a solenoid, so it's one of those coils of wire that we've discussed. So a coil of wire like so, connected to some kind of source with a positive and a negative, is called an electromagnet. So this is basically an electromagnet. As soon as a current flows from the positive to the negative, we get a magnetic field, and that magnetic field, remember, acts as a bar magnet, and it goes something like that. Okay, so you have to be able to draw this field around a solenoid or a bar magnet. Right, so let's talk about this question. Explain why it's better to use an electromagnet rather than a permanent magnet in a scrapyard. Right, well, the first thing is, because you can control the voltage or the power, if you can control the power, the voltage, remember power is equal to voltage times current. So by controlling the power, we're controlling the voltage and the current. If we can control that, we can control the strength. So we can control the strength of an electromagnet. What else can we do? We can turn it on and off, which is really important. So when you picked up the car, you want to drop it somewhere. If it was a permanent magnet, it'd be constantly attracting to the permanent magnet. So picking it up when it's on and dropping it off when it's off is a really important feature. The fact that we can control the strength means that we can pick up very heavy objects. So electromagnets are very strong. So because they are very strong, they can pick up heavy objects because they have a stronger magnetic field. Right, so in terms of permanent magnets, well, we're going to talk about the opposite. Permanent magnets, they're always permanent. They're magnets that cannot be turned on and off. So cannot be turned off, which is not very useful when you want to drop the car. So if you wanted to explain that, that will probably be better. And another problem is they lose magnetism. So if you remember when we did a magnet and we tried to align the domains all in the same direction by stroking a piece of magnetic metal with a magnet, you align the domains and that makes the material more magnetic. Well, if you knock this, which you're constantly going to do in a scrapyard, it will disalign the domains, and when they're facing in different directions, the field is not going to be as strong. So this one will have a strong magnetic field because the domains, these arrows, are all in the same direction. This one will not be as strong because the domains are all in a different direction. So in a scrapyard, this is exactly what you don't want to happen.